If you would recall, we've started our first big topic in vector calculus, and that's line integrals. In line integrals, we're going to integrate a vector field along a curve in R2 or R3, although this applies in higher dimensions as well. We're playing the same integration game that we always play. Multiplication, integration is multiplication, but one of the factors is continuously variable. In this case, both factors are going to be continuously variable, but that includes one factor being continuously variable. Because our factors are now vectors, our multiplication is now dot product. Our notation operates the same way it did before. We have the generic notation is the integral over C of f dot dr. The integral over C is the set of points that we're evaluating f dot dr. F is the thing that we're evaluating, the vector field. dr are small constant pieces of the curve C, the set over which we are integrating. This is the same as when we had the integral from a to b of f of x dx. The interval from a to b is the set over which we are integrating the function. The dx is some small pieces of the interval. We're doing the same thing. It's just now all curvy instead of a boring old interval. My Calc 3 teacher always said this is where calculus finally gets interesting, but I never heard him actually say that because I was usually asleep at the time. But that's the rumor. So we're doing the same thing, and that's why we're starting with this line integral. Integral over C. These are all the points over which we are going to evaluate. These are all the points where we evaluate f dot dr. F is the vector field that we're integrating. dr is small pieces of the curve. So if we have, if the curve, instead of imagining the curve as this continuous flowy line, we're just imagining this as a bunch of tangent vectors. At each point, we just take a note of which way the curve is going. Here, I am using n equals 4 tangents to describe this curve. Just like always in calculus, if we want a better approximation, we just use more pieces. But we imagine the curve as a bunch of tangent vectors that just keep getting smaller and smaller. Here's the curve, and we're imagining it as a bunch of vectors. So this would be like a dr1, dr2, dr3, dr4. Just like when we break the interval a to b up into a bunch of subintervals dx. So we needed some mechanics for this. We're going to parameterize the curve with a vector function, r of t, that we call r of t. Then we're going to write the dr as r prime of t dt just by taking the derivatives of the terms and then multiplying by the dt. So this first part, f at r of t, there we are evaluating the vector field at all the points on the curve. That's what's happening in that factor. And this is the dot product with r prime of t dt. The curve imagined as a bunch of vectors. So here's the dot product of tangents to the curve and the vector field at the point. So this factor f at r of t is the vector field at all the points on the curve C. And this is the dot product with what the direction of the curve. So we're imagining where the vector field is pointing, and we're imagining where the curve is pointing, and then finding the dot product of those two values. Any questions? Let's take a look at an example. So if we're going to play the line integral game, here are the elements I need to handle. I got to give you a vector field, and I've got to give you a path. So here's our vector field, 2i plus j. In this case, our vector field is not going to be continuously variable. We have a constant vector field. And we're going to calculate the line integral, where C is the quarter circle from 5, 0 to 0, 5. I picked this piece of a circle of radius 5 because we've already parameterized it. We actually parameterized all the way around, but here I just want the quarter circle from 5, 0 to 0, 5. I picked this because we've already parameterized it. So in this case, r of t is going to be 5 cosine of ti plus 5 sine tj. Since I only want the quarter circle from 5, 0 to 0, 5, I only want what's going on in the first quadrant. I'm going to run t from 0 to pi over 2. So this is the reason I picked a quarter circle, because we've already parameterized it. The other elements that we'll need here, I will need r prime of t dt. So I'll take the derivative. I'll find dr dt. So dr dt is going to be the derivative of each of these terms. The derivative of 5 cosine of t is negative 5 sine of t. The derivative of 5 sine of t is 5 cosine of t. We have the same restrictions on t running from 0 to 2 pi. Oh, and this is all dt. So dr dt is just r prime of t, and then we multiply by the dt. Find out just what the dr is. Any questions? Now let's put things together in the line integral. So the integral over c of f dot dr will be the integral of the vector field evaluated at all these points. So the 5 cosine of t is equal to x, 5 sine of t is equal to y. None of that matters because my vector field is constant. So my vector field is just 2i plus j. I find the dot product of the vector field evaluated at all these points and the dr, which is negative 5 sine of t I plus 5 cosine of t j dt. The other part of the parameterization is the values over which we are integrating, and that's from 0 to 2 pi. 0 to pi over 2. So one thing to note about this particular example is that the vector field in this case is constant. That's why there's no orange there. Notice that our integral has become just a regular integral of just one variable, a simple integral, a single integral. Right now, we've still got vectors running around, but there are both factors in a dot product. And once we do the dot product, we will have a scalar function. So this will result in a scalar function. So we'll get the integral still from 0 to pi over 2 of 2i times negative 5 sine of t. So negative 10 sine of t plus 1 times 5 cosine of t. So plus 5 cosine of t. And then we integrate this dt from 0 to pi over 2. Once we calculate the dot product, we're looking at a scalar function. There's our post dot product scalar function. So now we can just integrate this. So the integral of negative 10 sine of t is 10 cosine of t. The integral of 5 cosine of t is 5 sine of t. And then we evaluate from 0 to pi over 2. Derivative of cosine is negative sine, derivative of sine is cosine. Okay. Don't forget to distribute. I didn't want to write a bunch of extra parentheses. Now we just evaluate. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. Cosine of 0 is 1. Sine of 0 is 0. So we get 5 minus 10. We knew we were going to get a scalar because when we calculate a line integral, the product the product is a dot product. Dot product results in a scalar. Once we plug stuff into the line integral, we get a simple integral, a definite integral from A to B, and we know that that will result in a scalar. So we're not surprised that we got this scalar. We might be wondering, what does this scalar represent? And right now, it doesn't really represent anything because our dot product didn't represent anything. It was just a dot product. This was a mechanical exercise, lateral raises. Any questions on the calculation? How's everybody okay? Everybody looks so stoked. All right, we're doing vector calculus. Fuck yeah.
I mean, it could be good.
That's a great qualification. It could be interesting. But right now we're doing mechanics, and mechanics always puts us to sleep. All right, so this is just mechanics. Let's take a look at what this looks like. Let's think about what the, oh, I ran out of pages. I guess class is over. Just kidding. I have many more pages. Let's draw a picture of this vector field, and then you'll discover why I picked a constant vector field in this case. And then let's draw a picture of the curve over which we are integrating, and think about the dot product and how these things might be related. It's terrible because they say a picture is worth 1,000 words. And with me, I draw the picture and I still use the 1,000 words. It's like, well, Leach, if you're going to draw a picture, can you shut up for a minute? I'm like, oh, no. You'll get 2,000 words.
If you don't make everyone snore, you are not going to do that.
Correct. It's not a math class if someone doesn't fall asleep. All right, so we're only in the first quadrant, so I'm just going to sketch in the first quadrant here. Our path is going to go from 5, 0. Our path's going to go along a circle from 5, 0 to 0, 5. So remember, when we have a curve, a parameterized curve, we have orientation on the curve. So I'm going to try to draw a circle. Not going to be very successful. So I'm just going to be even more sketchy. And then I'm going to draw an arrow to indicate the direction of the curve. So there's the path C from the point 5, 0 to the point 0, 5. Now I'm going to draw in not the whole vector field, because that would just be coloring the whole paper blue, because I'm using a blue pen for the vector field. I'm just going to draw some samples. The vector field looks the same everywhere. It's always the vector 2, 1. So I have all these vectors 2, 1. So what we notice about this calculation is that the vector field is generally flowing from left to right, but our path is generally moving from right to left. So now we are not surprised that the line integral gave us a negative value. We're not surprised at all that the line integral came out negative. Because when we multiply vectors at an angle, and the angle between those vectors is more than 90 degrees, our cosine is negative, our dot product is negative, we're multiplying two values against each other. The path is going against the flow of the vector field, generally, overall. The path C is generally going against the flow of the vector field. Mostly. Because we also noted, so I cast this and said, generally the vector field is flowing from left to right, but the path is trying to move from right to left. And so that says there should be negative. But if we think about the y-axis, the vector field is generally flowing up, and the path is generally also going up. So it's mostly going against the flow of the vector field horizontally. It looks like the horizontal part is winning because we got an overall value of negative. We draw little vectors, little tangents along our curve. At least horizontally, we can see that this path is trying to go against the flow of the vector field. Let's suppose we grab a different portion of this circle and recalculate our line integral. Now we've done a lot of, I want to use the same circle so we don't have to do a lot of extra calculations. Some people say this is me being lazy. I say this is me being efficient. That is true. Lazy is the efficiency that we apply to people that we don't like. When it's people that we don't like, we say, oh, they're lazy. When it's people that we like, we say they're being efficient. See how it works? So let's try. Let's go with the same vector field. Let's go with the quarter circle in quadrant 4 from 0, -5 to 5, 0. We're just going to change the endpoints. We have the, I'm changing what C is, but our parameterization is still the same. R of t will be 5 cosine plus 5 sine. But t will now go from, we got a few options. We can go from 3 pi over 2 to 2 pi. Or we can go from negative pi over 2 to 0. I don't know. It depends on what you think of. What the best one to use is whichever one you think of first. The reason that I picked 3 pi over 2 to 2 pi is that right after this class, I teach a trigonometry class. So I live my life from 0 to 2 pi. It's like living your life a quarter mile at a time, only circular and a lot less movie work. All of our previous calculations still hold. Our integral over c of f dot dr. What's going to change is that we'll integrate from 3 pi over 2 to 2 pi instead of from 0 to pi over 2. We can even skip the dot product portion and go straight to the function that we integrated, negative 10 sine t plus 5 cosine of t dt. That part of the calculation, the dot product part of the calculation isn't going to change because I'm using the same circle, just a different section of it. Just changing the interval over which we integrate. And we also try to cram it into half a page, even though I knew it wouldn't really. So in this case, sine of 2 pi is 0. Cosine of 2 pi is back to 1. Cosine of 3 pi over 2 is 0. And sine of 3 pi over 2 is negative 1. So now I have 10 minus a negative 5. Now we got a positive value. Let's think about what this looks like. We're only in the fourth quadrant, so I'm just going to draw the fourth quadrant. Here's the path going from 0, negative 5, 5, 0. Our vector field is still a bunch of 2 1s. Now, in this case, we see that the path C is not only going with the vector field from left to right, but also with the vector field from up to down. So horizontally and vertically, this path is traveling in the same direction as the vector field. So we get this large swing from negative to positive, and not just the amount, we got a large swing of 15. Moreover, we can see where this 15 came from. We can see where the imbalance came from. This vector field is more horizontal than it is vertical. It's 2 horizontal and 1 vertical. Here's that 2 horizontal counting twice as much as the 1 vertical. So in this case, the path C So it looks like in the previous problem, we had 10 in the horizontal, 10 in the, a negative 10 in the horizontal, and then positive 5 in the vertical, because they are at odds, horizontally going against, vertically going with. But in this case, our horizontal and our vertical are both going with. 10 from the horizontal, 5 from the vertical, going in the same direction, total of 15. So at this point, if I switched the next problem, or the next path to be the quarter circle in quadrant 2, we could predict what the value would be. If we switch from the path from to the quarter circle in quadrant 3, we should be able to predict what the line integral would be. Any questions? How's everybody okay? Everybody looks so stoked. You all look like this. I imagine that's what you look like when you're stoked. Like you could be at a concert from your favorite performer and you'd be like, oh.
Must be the greatest poker face.
So I don't play poker with my students. Any questions? Comments? Snide remark? Yes. Yes. Oh, got it. How's everybody okay? All right, so what we want, what the calculation part, that's just the troublesome part that we have to do to make sure that our intuition is working. The intuition that we want is we want to think about integration as multiplication, but one of the factors is continuously variable. The new thing that we have is that the multiplication that we're using is a dot product. So our understanding of line integrals is going to be dependent a lot on our understanding of what the dot product can be used for. That's going to be based on our understanding of how we think about the dot product. The dot product is multiplication at an angle. When our quantities are in the same direction, theta is equal to 0 between them. Then cosine of 0 is 1. And so we just get all the magnitudes of both factors. As cosine goes from 0 to pi over 2, our product drops from the full product of the magnitudes down to 0. When two quantities are moving perpendicular to each other, they're not helping each other out. They're not hurting each other. They're not helping out. It's just nothing. And then as theta goes past 90 degrees, past pi over 2, then cosine goes negative. Our product is negative. We can interpret that as the products, or the factors working against each other to produce a negative result. Different direction. That's everybody okay? I know I said that dot product stuff a lot. because songs don't get stuck in your head because you heard them once. Songs get stuck in your head because you can't avoid them for a period of time. Or you want them. Any questions? It's just math is not as catchy.
This is the-
It's just going against, going with. That's the way that we're going to think about it. Going with, that produces positive dot product. Going against, that produces negative dot product. We just need to hear this, think about it, say it to ourselves a bunch of times. Because, like I said, it's not catchy. This ain't Texas. Okay, I just put a song in all of your heads. Most of your heads. Depends on how much you've been around the internet. All right. This is what we want to think about with line integrals. I want you to remember that this is the same calculation that we've always been doing. We've just upgraded from our multiplication from just regular plain old multiplication to the dot product because our factors are vectors now. And that's one of the ways we multiply vectors. All right, that's going to do it for today. Everybody have a good day. I'll see you all on tomorrow. And thanks for playing.